Welcome back. In the last lecture, we saw some of the techniques for content distribution in the IP network. So we said that the current IP network is designed for point-to-point communication, and then because the applications are there, they are doing the multi-point distribution. So some of the things that were designed and retrofitted into the point-to-point communication. So particularly the CDN networks, the caching techniques, be it the proxy server level caching or the network service providers doing the caching, and some of the peer-to-peer networking mechanisms. So all of them we saw. So the summary of the discussion that we had in the previous lecture goes something like this. So IP network is fundamentally a point-to-point communication. So it is meant to deliver the content or transfer the content from the point X to Y, and using that underlying communication mechanism, I am actually building an application which is doing the multi-point distribution. So although many of these techniques that we discussed, like the CDN networks, actually improved the response time and the localized the content storage to a large extent, bringing efficiency, but still the underlying mechanism, the transmission that is going on, is still point to point using the point to point communication. So that's the inherent efficiency of the point to point communication is still existing in the underlying network. So because the IP network is actually point-to-point communication, and it has been engineered to work in a stateless fashion. So what I mean by that is, if X is the one which is transmitting the content and Y is the receiver, and there are a bunch of intermediate routers. So if X transmits, let's say, a packet P1 to the receiver Y, and if he X decides to transmit the same packet, same content 1000 times, the network blindly transmits that content 1000 times. In effect, what I am trying to say is, R1 doesn't remember whether the packet 1 has been previously transmitted from the same source to going to the same recipient. So if let's say P1 is carrying an image, and the same image is getting transmitted 1000 times to Y, that's the inherent efficiency. And the inefficiency, in the sense we are looking from a perspective which is the usage perspective in today's networks. So but back then this was the best choice one could have made, and that's how it has been engineered. So it is stateless and works in a fashion which is something called as statistical multiplexing. So what it means is, if there are multiple senders X, maybe an A is also sending, the R1 looks at what is the available bandwidth, the bandwidth on which the packet has to be transmitted, and if there is bandwidth available, it will simply transmit that without differentiating whether X is transmitting giving the packets, or A is giving the packets. So both of them, from the R1's perspective, they are same. So as long as there is capacity to transmit, you simply transmit. That's the statistical multiplexing means. So at some point, if only X is transmitting, then the whole bandwidth available for transmission is given to only X transmission. So that is the best approach that one could have used, to given the scaled resources. Scaled resources in the sense, here it is the both the ability of the R1 to process those packets, perform the lookup operation, and then also mean the bandwidth available at the R1's disposal to transmit the packets. So this is still there. We are still using the same underlying mechanism to do the transmission. So that is a cause of worry for us because of the efficiency. So now this kind of the communication, whatever is there in the IP network, is because it is stateless and it is doing the statistical multiplexing, it opens the doors for several cyber attacks as well. So for example, if X is having a malicious intent, and he want to bombard Y by sending multiple number of the packets, let's say 1 million packets per second he is transmitting without any purpose, nothing actually prevents X from doing that. So, in the case the Y doesn't have any control over what it can receive, unless a simple thing that it can do is maybe it can filter the traffic from coming from the X. But if X is not using its own IP address, if he is randomizing the IP address and then sending those packets, then Y has nothing to do at its disposal with which it can actually safeguard itself. So it becomes a hard choice for the Y to mitigate this particular traffic. So that is the one another issue that you have in the current IP network. So, with that background in mind, let's see what the information centric networking is all about and what are the design goals and objectives for this information centric networking. So, if you recollect the previous lecture discussion at the end, what we said is a user wants some content. So, he wants an image, he wants a video, he wants some audio content to be delivered to itself. So, but then how do I actually deliver that content? So, yes, a communication model which is centered around the information or the data is what we are looking for. So, that is precisely what the information centric means, is information centric networking means. You keep the information at the center of the communication, and around that you build the mechanism to do the transmission and the distribution. In simple terms, that is what it means. So, let us see how that information centric networking is supposed to work, at least in the idealistic scenario. So, what we have in this picture is a server. So, that is where the content is actually produced, and somebody who is interested in receiving that content. So, the guy on the left hand side actually makes a request. So, I want content C1. So, assuming C1 is available at this server, he says that to the network in the sense to the nearest router to which the client itself is connected or the user is connected. So, he asks, can you give me content C1? And the network or the router figures out where exactly C1 is. So, there is nothing called IP address, there is nothing called a TCP connection from the client and the between the client and the server. All that the client asks is to the network, I want C1. It does not matter from where you bring it from, can you give me C1? That is all it says. And the router internally knows how to figure out where exactly C1 is, or the host which actually has the content C1, and then it forwards the request, client's request to another intermediate router which is closer to the content where the content is available. So, here in this case the server is the one which is having the content, so it is actually forward that request to the server. So, not necessarily only two of them, but through a bunch of intermediate such routers, so who can actually understand what is being requested and where to find out that content. So, the request finally goes and reaches the content producer, and the producer in response to that sends the content back in the reverse direction. So, first if you name this router as the R1, then this router as R2, the response, the content C1 first comes to R2 and then it goes to R1, and finally it is delivered to the requester. So, the client which actually made the request, the content is delivered. So, now the role of the R1 and R2 here is, when the content is going in the reverse direction, they also make a very informed choice to keep a copy of that content C1 within its own store. So, that is in effect what it means is, every router not only have an understanding of what content is being requested and where exactly the content is presently, and they also have an inbuilt storage mechanism where you can actually store the content, here in this case C1. So, assuming for the time being both R1 and R2 make a choice to store the content C1 when it is forwarding the content in the reverse direction, If subsequently another client, here in this case the client at the bottom of this figure actually makes a request to R1, so instead of going to the server on the right hand side, what it does is it responds back supplying the copy that is stored in the previous communication. So that's actually a very nice thing. So assuming the content producer is some 20 hops away, so the client in the second case actually getting the content in one hop communication. So that is actually a very nice thing to have. So by virtue of this ability to cache the content and then an ability to do and the forwarding operation by looking at the content requests, so you actually minimize lot of work that is happening in the network. So this is what we call it as the information centric networking. So you keep the everything is happening in terms of the information, in terms of the content, keeping that content in at the center of the transmission you are actually operating. So now this is what we exactly want. Let's formalize this ability of this network in terms of some characteristics, what exactly we want to achieve, what are the design objectives of such a network. So one of the primary objective is to improve the content location, in the sense that what I mean by that is in an idealistic scenario, no matter who is actually requesting the content, whether it is the client 1, client 2, client n. So all of the requests made by all these clients in the entire global network are supplied by or serviced by the routers which are actually closer to the requesters themselves, in the sense that whether if C1 clients 1 request, the first hop neighbor of the client 1 is able to service its request. When client 2 makes a request for some other content, not necessarily the same content, that time also I will be able to do the servicing or get back with the content to that client within one hop communication. So every request is serviced by not more than one hop communication. So in effect, what I am trying to say is, wherever the clients are located and the nearest routers have all the contents that these clients are going to make in the future. So that's an idealistic situation. We want to, by arguing that we want to keep a copy of the content, what we actually wanted to achieve is this one. So every content request originating from every client would be serviced by the the nearest router that is connected to the client itself. So we want to achieve this. Whether we will be able to achieve this or not is a secondary question, but this is where we want to be, at least idealistically. And second thing is, since we keep a copy closer to the client which is actually consuming that content, so this brings the delivery efficiency. So in the previous scenarios what we discussed, many times the same content is being transmitted over the network, that brings us the redundant data transmission. So that is actually avoided. I want to achieve a zero redundancy transmission, at least idealistically. That is the second objective of such an information centric networking. And then, since as a byproduct of this operation, I am keeping many copies in the network, many of the routers have a copy of the data transmitted. So there is inherent redundancy, and that replication actually brings the or improves the availability. For some reason, if the original producer or some other router in the network having a copy is not available or down for some reason, then you can actually go elsewhere and then find out the same content. So C1, if let's say R2 is down for some reason, somebody who is connected to, let's say the client 3 wants to access that content, assuming it has got connectivity or it can go and reach the R1 through some other link, it can still find out the content R1 within the network. So that's what we want to achieve, is by replicating the content or intelligently caching the content at different locations in the network. We want to improve the availability of the content itself. And unlike the current scenario of the data delivery, where the security notion is a tunnel that exists between the data consumer and the producer, we want to depart from that notion of the security, and what we want to achieve, at least idealistically, is every piece of data that exists in the network and delivered as response to any request originating from any client is guaranteed to be generated from the authentic source. That's what we want to achieve. So doesn't matter whether the router R1 service provides that content or router R2 provides the content, or the original data producers, the server itself actually delivers the content. So all of them every copy that exists in the network can be verified to be generated from one source, which is the authentic source. That's what the design objective is. So these are the idealistic objectives of such a network, and then how do we achieve this is the secondary question. So let's go and see what are the these objectives that we put forward have translates into something called as the design goals. So what we said, access the content regardless of the location, meaning that the client really doesn't care whether the content is available at a router which is directly connected to it, or at a router which is 10 hops away, or a producer which is 20 hops away. So all that he knows is what content he wants. So there is a movie xyz dot something file extension. So the client asks, can you give me this movie xyz dot something? And then the network figures out where is that xyz dot maybe in MP3 or whatever the extension is, MP4 or something like that. So client really doesn't know where the content is, and it should be able to access that content without actually establishing a connection to that host which is actually having the content. There is nothing like a TCP connection going from the client to the place where the content is located, be it the router or the one of the data producer. So that ability we want. So this goal is coming from the objective that we put forth in the last slide. And because the client is asking, all that it is asking the network is, can you give me this content? It is identifying, it is proposing a name, and using that name the network is actually delivering the content. So in effect that means that the network knows what is the naming convention, and it understands what a particular name means. So for example, if it is asking, can you give me a movie which is 1.mp4, and then what is 1.mp4, the network knows. The router R1 understand what is 1.mp4, and the router R2 also understand what is 1.mp4, and every router in such a network understand what is 1.mp4. So everything is operating in terms of the name. That is the second design goal. Now how do I make the routers aware that to operate using such names is the question. And it also means that you also have a name based identification of the content, and the routers know how to forward the request using the names and store what is there inside my own cache, because every router is equipped with a storage that is called cache. So what is there in my cache, what is there in my neighbor's cache, and what is there in the router which is 10 hops away, everything every router, at least in idealistic scenario, should be aware of. And the third is, even when I keep a copy of the content in one of the router, the security of that content should be preserved. So and these are the end goals. How do I actually achieve this in practice? And then we want to separate out the data that's actually the naming convention is from the client's perspective. When you forward the request from the client to the nearest available content store, be it the router or the producer. So, these are the abilities you require. You require naming, you require name based routing, and you require the content security. And from the other perspective, when the data is actually moving and getting cached in the reverse direction, you don't want to attach a location to that data. It doesn't matter whether the R1 caches it or R2 caches it or R10 caches it, all of them caches it. So, I don't want to tag a particular piece of information, a particular piece of the data at any location. Location in the sense, here you can roughly map it to the IP address. So, any data content should not be mapped to one particular location. By virtue of caching that content, you can actually go, any of the router can go and ask, okay, you have this content, can you give me that? That is a different story. But I don't want to hardcodely tag a particular piece of information to one of the IP address or the location. And it doesn't matter which application is consuming that content, and what kind of the transport protocols or the mechanism that we use to carry that content, even from the producer or the location where exactly it is currently residing to the intended recipient. So, these are the end goals. So, everything is operating in terms of the name, and then there is nothing called one particular host or a particular host or a particular router which is actually having the content. There is no tagging connection between this name and this content storage. So, that is what the end goals. Now, these are the things that we want to achieve. Now, the question is, how do we actually achieve this? So, is it possible in the IP network? Maybe or may not be. So, the answer to this is, how do I translate these design goals and objectives into reality? Is it boils down to revisiting some of the fundamental concepts that were used in designing the TCP/IP network. So, in the current TCP/IP network is operating something on a semantics called send and receive mechanism. Somebody wants to send a data, a piece of information to someone else, he can send it. So, if my computer wants to send a packet to someone else's computer, if I know the IP address of that computer, I can really send that particular piece of information. What he does with that information is a secondary thing, but as long as my intent is to transmit that packet or the data to that recipient, I can still do that. And we want to depart from such a semantics where the sender has got an absolute control over what he can send to whom, to a semantics where the consumers can control what it can receive. So, meaning, if I am interested to receive the packets or the data from originating from a particular source or a particular type of the content, I should be able to do that. From a sender controlled approach to a receiver controlled approach, that is what we want to achieve in practice. So, this is what we want achieve, is the receiver driven operation. So, if I do not want to receive some sort of the content, I should be I should not be receiving that content. That ability we want to bring in. And if I am interested in only a particular type of the content, so I can subscribe to that particular piece type of the content and get only that content type of the content. So, in the previous lecture we saw how the publish subscribe mechanism works, where any data producer will tag the content with a particular name and or the topic, and the subscribers actually show interest in receiving such type of the content, and whoever has shown the interest, the content will be delivered to them. So, we want to move to that kind of the semantics. So, the publisher here does not have any control over to whom all he can push that content to. So, the receiver have got the complete control, what it want from whom, which topic, content of the what type he wants to receive in. And then the third conceptual revisit that we want to do is from establishing a connection so between two hosts which are connected to the network through some intermediate routers. What we want to do is just the some of the host actually makes a request to some of the content, and the network knows how to search that content and figure out what is the nearest place I can get the content, whether it is 1 hop, 2 hops or 10 hops. From there it pulls out that data and then gives it to the intended recipient who has made the request. And we don't want to establish a secure tunnel. Instead of that, we want to secure the content itself. So I want the authenticity of this content is originated from the so and so source from whom or whose content I as a consumer want to consume. So since this is we are talking about the content distribution, so that's a multicast operation. A subset of all the recipients globally exist will be interested in content generated by some producers. So from a unicast model of the communication, we want to go to a purely multicast transmission semantics. So these are the fundamental revisits that are required, or the differences that exist between the IP networks and an idealistically designed information centric networking. So these are the things that we want to achieve. So now how do we achieve it? So as an answer to whatever we discussed in the previous slide are all the design choices are the fundamental things that exist in the networking, and then in order to translate those requirements into reality, several research projects actually started, at least in the last decade or so. So these are some of the research projects that actually are exploring the how exactly we can realize this information centric networking. How do we bring the ability of the storage? How do we bring the ability of the naming the content? How do we do design routers which are aware of analyzing or retrieving the content based on the names? So there are people are exploring different mechanisms. So although we don't have at this point of time a particular method which is actually working in practice, or at least having shown the promise, but there are many parallel projects and exploring the different directions of achieving these research objectives. So you can many of them in fact have the websites where you can visit and then explore the details of what exactly they are bringing. They are proposing the different architectures for the such a network, which is actually operating on using the content as a central piece of mission.